And I'm going to begin by talking about zero forcing and its variants. Zero forcing is a process, it's a dynamic process, you can think of it, for coloring vertices on a graph. It represents a lot of different particular applications. As we're going to talk about it today, you start with blue vertices and white vertices, and the goal is to color all the vertices blue. You can change the color of a white vertex to blue, but once a vertex is blue, it will always stay blue. And the standard color change rule is that a blue vertex can color its white neighbor if it has exactly one white neighbor. There are many different variants of zero forcing, and the difference here will be the color change rule. As I mentioned, zero forcing grew out of applications. One of the first applications was power domination, and this actually predated the study of zero forcing. So power domination is modeling on a graph an electrical network, and you have phasor monitoring units, and there are certain rules that for what these units can observe directly and for what these units can observe by solving systems of equations. And it turns out that the direct observations are domination, meaning you observe all your neighbors. And then if you treat those vertices as blue or observed, then you can proceed by zero forcing, as just described. When there's exactly one white neighbor of a blue vertex, it can be colored blue or it can be observed. And this is really critical to maintaining safe and stable electrical networks. Another original introduction of zero forcing was through the control of quantum systems in mathematical physics. This was in about 2006, and the power domination was much earlier. The seminal paper that introduced it by Haynes et al. Was in 2002. And the third application that is the one I'm going to focus on for the variance I'm talking about is in combinatorial matrix theory. So as Sandra mentioned, I have a strong interest in linear algebra, and especially the interplay between matrices and graphs. So for our purposes, all our matrices are going to be real, and they're also going to be what I call combinatorially symmetric, meaning that if aij is non-zero, then aji is non-zero. And this, of course, covers a symmetric matrix where the ij and ji entries are equal, and a skew symmetric matrix where the ji entry is the negative of the ij entry. And most of the matrices I'm going to talk about will be symmetric, some will be skew symmetric. And you see here a notation for the set of n by n real symmetric matrices. For a given matrix, we can draw its graph. So here is a matrix, and you see that it has non-zero off-diagonal entries in the 1, 2, 1, 3, 1, 4 positions. And so in the graph, I draw edges between 1, 2, 1, 3, and 1, 4. And we just ignore the diagonal here. So for standard zero forcing or the standard inverse eigenvalue problem that I'm going to talk about, we are not paying any attention to the diagonal. So as I just mentioned, the big overarching problem for these matrices in their graphs is to determine the possible spectra or sets of eigenvalues of the family of matrices described by the graph. So you pick a graph G, and then you consider all real symmetric matrices that have this particular given graph G. And the inverse eigenvalue problem, or IEPG, is determine all possible spectra of these matrices. So there's an example here, a matrix that is described by the path and 3 vertices, and you have 2 non-zero off-diagonal entries, and you have 3 diagonal entries, which can be 0 or non-zero. It's not terribly difficult to see that all of the eigenvalues must be distinct, because if you were to delete the first row and the last column, you would have a matrix, and I'm actually just going to switch over here and stop the screen share and show you what I'm talking about. So I think you want to spotlight this so that people will see it, Sandra, because I'm seeing something different on my screen. Anyway,
I'm not sure how to spotlight it. Let's see. Oh yeah, spotlight video. There it is.
Okay, thank you. So we had X, A, 0, A, Y, B, 0, B, Z. This is our matrix. And what I'm going to do is I'm just going to strike out the first row and the last column. And now I have a nice little matrix here. And what you see is that the A and the B have to be non-zero. And so this means that this matrix right here automatically has rank 2, or nullity at most 1. And a critical feature for the inverse eigenvalue problem is the fact that the maximum eigenvalue multiplicity and the maximum nullity are the same thing. And so if you, this is on this slide, you see this, we identify M of G as the maximum multiplicity or the maximum nullity. So what this example that I just showed you in the previous slide, or the, here we have it, I had it on the dot cam a minute ago, but I think we argued that the rank here of this matrix must always be at least 2. That means, and it doesn't matter if I take an eigenvalue and take A minus lambda I only change the diagonal, and my comment remains valid. I can't have a multiplicity greater than 1. So all the eigenvalues have to be distinct. So that's relatively easy to see. The fact that you can have any set of 3 eigenvalues is not something I'm going to explain right now. It's a lot deeper result. So here we have the definitions of maximum nullity and minimum rank. And the inverse eigenvalue problem is so challenging that typically it has been approached by subproblems, such as finding the maximum multiplicity rather than trying to find the entire spectra. To give you an idea, there are dozens and dozens of families of graphs for which the maximum multiplicity or maximum nullity has been determined. There are probably less than 5 families of graphs for which the entire inverse eigenvalue problem has been solved. And the entire inverse eigenvalue problem for small ones is only solved up through order 6. There's software that for maximum nullity will probably get you the result for anything up to 10, maybe with a little bit of extra work on your part by hand, but it's a much more tractable problem, although still not easy. So what's the connection with zero forcing and maximum nullity? It's in this theorem here, this extremely long list of authors, which this paper is normally known as AIM 08. So this was, there was a workshop held in 2006 at the American Institute of Mathematics in which this was one of the problems investigated, and zero forcing was actually introduced in the manner we're talking about today at that workshop, although as I say, it arose independently in other contexts. And here you have the definition of the zero forcing number is the minimum size of a zero forcing set. A zero forcing set is a set of initial blue vertices that can color all the vertices blue through the zero forcing process. And this is related to maximum multiplicity or maximum nullity because it is an upper bound. And this is sufficiently easy that I can actually, what you see here is an explanation of why it's called zero forcing. So you start with a graph and you start with a null vector x. So this x here is a null vector. So ax equals 0. And we have the coordinate of the null vector is 0 for all entries of the currently blue set. So this is not necessarily what we started with. It's whatever are blue right now. Then we have an I in the blue set such that there is a J that's not in B, meaning we don't yet know that that coordinate is 0. J is the only neighbor of I that has that property. And together, this implies that xj must be 0 because we just equate the ith entries. We look at the ith coordinate equation here, and you're only going to have the entry aik be non-zero when it's a neighbor, and in that case we know ak is 0 if it's not a neighbor. And the diagonal entry, we already know, I mean, the ith entry is already 0 also because we don't know that the diagonal is non-zero. So this is, we are literally forcing zeros in a null vector. Then to get the upper bound, you use some linear algebra that basically says you can't be able to predetermine too many zeros in a null vector if you're able to do that in a non-zero null vector. And that's what gets you the upper bound. So here I'm going to illustrate for you the zero forcing process on this particular tree. As we've said repeatedly, the standard color change rule is that a blue vertex can change the color of a white vertex W if it's the only white vertex that is a neighbor of V. So here we have a graph with blue vertices, and you see this blue vertex on the upper right has, can you see when I'm pointing here with my little mouse or not?
Yes, we can see.
Okay,
it.
good. So this has one white neighbor, so it's going to force. This one's not going to do anything, but this one's going to force, and this one's going to force. So that's what happens on the next slide, and now we have a bunch more forces that can take place, and we force the entire graph. Now, what I just showed you is not actually the original way zero forcing was done. So a more sophisticated perspective is to perform simultaneously all forces that can be done independently that rely only on the currently blue vertices. And that's the perspective I've taken here, and that's going to be very useful as we move on to propagation time. But originally when zero forcing was introduced, it was done one force at a time, not doing several forces as I've done here. One thing that's worth mentioning is if you look at the previous slide, I just blithely said that the zero forcing number is 4. Well, we didn't actually prove that. So here we have this tree, and we showed that 4 vertices is enough to force. We don't know that that's the only, that there isn't a smaller set. And it is a theorem that the zero forcing number is equal to the path cover number. A path cover is a collection of disjoint induced paths that cover all or partition all the vertices. And there's an outside in algorithm for trees. And so I'm just going to show you on this picture. So this is what's called a pendant generalized star or a pendant spider. And I'm just going to cover it with a path. And then I'm just going to delete it from the picture. So this is 1. And then down here, I have 1. So that's another 1. And then right here, I have another 1. And 1 here. And what you see there is that I actually have 4. So this is the way we show that the for this particular tree, it actually is 4. You can't do better. By the way, I just think this algorithm, which actually predates zero forcing, it was done for maximum nullity and path cover before we ever introduced zero forcing, but then it was shown that for a tree, all these parameters are equal: maximum nullity, path cover. It was known that path cover number and maximum nullity are the same on trees, but then it was shown that it was the same for zero forcing number. So one of the things I want to do today, as I mentioned, I'm taking a sort of more mature approach to zero forcing and exposing you to it as it's studied today, rather than it was originally introduced. And one of the perspectives that we use today is to compare and contrast different variants of zero forcing. So that's one of the things I want to do today. And these variants are defined by their color change rules. That's where the distinction comes in. A color change rule allows white vertices to be colored blue under specific conditions. And we proceed as we did with standard zero forcing. We define B0 to be the set of initially blue vertices. The set of blue vertices B square brackets T after round T under this color change rule R is the set of blue vertices after we apply the color change rule independently, starting with B T minus 1 as the set of blue vertices. And we say it's an R0 forcing set if there is a T such that we eventually color all the vertices, and the minimum size of an R0 forcing set is the R0 forcing number.
I'd like to ask a question about
Sure.
that. You obviously, the number of steps required to get to V of G can depend on the initial set. And
Yes.
how does that play into the discussion?
Yes, so one of the things that to get from the initial to the completely blue, that's actually the next topic we're going to talk about, which is the
Okay.
propagation time.
So there should be some sort of inverse relation between size and propagation time.
Relation is probably too strong a word.
I'm not using it in a technical sense.
Yeah, definitely. In general, if you have more vertices, you will go faster, yes.
Okay, but you'll discuss that later. Okay,
absolutely.
Thank you.
Good question. Other questions? And please do interrupt me if you have questions. That's great.
Leslie, is it obligatory to apply the rule as soon as it can be applied, or can you wait if you want to?
So that's a very good question. As I've just described it, you automatically apply it. And
Okay.
the perspective I'm taking is what I alluded to, which is propagation time, to do it through a propagating process that moves just as fast as it can, and you never wait unless you have to.
So the greedy algorithm.
Yeah, there is another perspective, which is actually the original perspective on zero forcing, where you get to choose which next force you're going to do. And you have a list of forces in order called a chronological list of forces that are done exactly in that order. And there are situations where it's useful to take that perspective. Other questions?
That original perspective sounds like before multiprocessing.
It was just, yeah, this is not really about implementing on computers, but yes, that's a nice parallel. So anyway, I'm going to talk today about two different variants, both matrix motivated, which is why I introduced the matrix motivation for the zero forcing number. So this is associated with positive semidefinite matrices and then later skew symmetric or weighted adjacency matrices will be the third variant we're going to look at. So the maximum positive semidefinite nullity refers to positive semidefinite matrices And a real matrix is positive semi-definite if it's symmetric and every eigenvalue is non-negative. And we have a notation S plus of G for the set of positive semi-definite matrices described by a graph. And we define the maximum positive semi-definite nullity as the maximum nullity among those matrices. You'll notice there's something missing here, and that's maximum multiplicity. This is no longer maximum multiplicity. This is the maximum multiplicity of the zero eigenvalue only, because you could shift up away from that zero, but then you'd have no nullity, or you can't shift down because you can't make negative eigenvalues. So we've lost that aspect, but we certainly have the maximum multiplicity of the zero eigenvalue or the maximum nullity, and that's what's being studied here. The positive semi-definite zero forcing number, which I will describe in a minute, is the graphical combinatorial upper bound in the same spirit for the maximum positive semi-definite nullity. It is a theorem. You'll notice that I don't have any sketch of the proof here, and that's because it involves some extremely deep linear algebra involving what's known as the column inclusion property, and it's outside the scope of this talk. So I want to just define the positive semi-definite color change rule for you and illustrate it. So we're going to use the same color change rule, but we're going to apply it a little differently. We're going to start with the set of blue vertices, and we're just going to think of cutting them out of the graph. And if you see here on this blue vertex in the picture, if I delete that, I get 3 separate components. A little tree of 4 vertices, an isolated vertex, and a bigger tree with 6 vertices. And then we're going to put this blue vertex back in separately on each component, put the set of blue vertices in and say, now, are we able to perform a standard force on this subgraph induced by the white vertices in one component and the set of blue vertices? Now, in a tree, that's immediate, because you will automatically have exactly one neighbor in that component, and you will perform all of those forces, as we see in the next slide. And as we just progress out, we're going to have what my PhD student Mike Ross calls full forcing. Every blue vertex just forces its neighbor. That's because this is positive semi-definite and it is a tree. That is not true in general, just for trees. So we can force that whole tree. And you see then that we have a zero forcing number 1. Since a vertex must be blue in order to force, that's obviously the zero forcing number. No further explanation needed. Any questions about positive semi-definite before I move on to skew? Okay. A matrix is called hollow if it has all zeros, and as I'm going to use hollow, it's going to be a hollow symmetric matrix. So I just want to avoid having to repeat the word hollow, so I'll use hollow to mean hollow symmetric. Skew symmetric matrix automatically has 0 diagonal. So we have the 0 diagonal on either a hollow matrix or a skew symmetric matrix. And that gives us additional information when we're going to perform these forces. We no longer need to have the diagonal entry have a 0 coordinate. In other words, we don't have to have a vertex be blue in order to force. And we define the maximum hollow nullity and the maximum skew nullity as the maximum nullity amongst these families. And as you see there, this is, and what's missing from this slide that I need to add is actually the skew forcing rule, because it's a little confusing to have the theorem without the definition. But before I send the slides to Sandra, I will add this 0 forcing rule to this slide. But it is on the next slide, the skew color change rule. Any vertex that has exactly one white neighbor can change the color of the white neighbor to blue if there's exactly one white neighbor. And so then you get The maximum skew nullity is less than or equal to, and again, these should be Z minuses right here. They're not Z's, they're Z minus. And it's the exact same proof that we went through already, but now we don't have to worry about the diagonal because, I mean, about the ith entry, the thing that we were saying had to be blue, the forcing vertex, because now we have the diagonal 0, so that one gets wiped out just like a non-neighbor. So now we can watch this actually play out on a tree. The very strange thing is, now this tree has 2 blue vertices colored, but in fact, it is possible to color an entire graph with no blue vertices initially, and I'll show you that in a minute. But here we have every vertex with one white neighbor is going to perform a force. So this vertex will force, but so will this one and this one. We have lots of vertices that forced, and now in 2 steps, starting with 2 blue vertices, we got that whole tree colored. And
Could you
this
go
is
back and show that again?
yes. So
There's
we
something-
start here. So this blue vertex can force, this
That's
white
clear.
vertex can force.
What forces the pendant vertex?
Well, right now, nothing has force-dependent vertices.
Oh, that's the next step. Okay, thank you.
Yeah,
No, I
actually,
missed the steps. Thank you.
but I think there's an error here, it looks like. I think you've caught an error
No,
because,
no, I didn't. You did.
oh no, you're right, because these force each other, they have only one. So this one can force dependent one, even because all of its other neighbors are blue, yeah. Okay. Any questions about that? Okay, then I just want to show you this example. I can take any graph. In particular, I can take a complete graph if I want to, and I can put on a pendant vertex on each original vertex. And now all of a sudden, so this is what's called K4 corona K1, and the skew forcing number of this is 0. Because I can force in here like this and color that vertex blue, fill that vertex. If I had thought better, I would have brought more of my colored pens. I do have some, but anyway. And then we can do, after that's all done, then we can go back out in 2 steps. So this is a very unusual situation because you can have 0 forcing number 0 for skew, which is in some regards a little strange. So any questions about skew forcing? Okay, so I'm not going to read this very long slide. This is just to give you a small sense. This is maybe 10 or 20% of what is known about these 0 forcing numbers. They're known for both the 0 forcing number and the maximum nullity and the positive semi-definite and the skew and the hollow. All of those parameters are known for complete isolated vertices, complete bipartite, path, cycle, and the list goes on. If you're talking just about 0 forcing numbers, those are readily computable with some software. I'll say something about that in the end. Maximum nullities are a little trickier. The standard has way more graphs known. The hollow and skew maximum nullities are probably the least done. Not that they're harder, they just haven't had as many things done so far. But there's a lot of stuff known here. And these 4 papers previously cited, these are the ones for the maximum nullity is less than or equal to the 0 forcing number. And there were 2 of them for skew forcing because we have both skew matrices and hollow matrices. So the next topic is propagation time. Before we do that, are there questions?
Leslie, For skew forcing, is it the case that every tree has zero forcing, the number zero as long as it has 2 or more vertices?
No, if you look at this one, the number was actually 2,
Oh, really?
not 0. So if we look at this tree, if we go back to the original picture,
All right.
what you can do is you can force in here, force in here, force in here, force in here, and force in there. And now you would be stuck because this one would not be blue. And this one would not be blue. So this,
Wait, but those would be the only white neighbors of a.
and so you'd be able so this vertex and these 2 would never get forced. So these 3 on the left, they would get forced.
Right. So the rule says that any vertex can change the color of a white vertex if it's the only white neighbor, right?
Right.
So after you put all those blue vertices in, these white guys that would remain would be the only white neighbors of some vertices. So in another round, they'd all be blue, right?
No, so let me just switch out of the screen share.
I must not be understanding.
Okay, so what we're going to have, these are all starting white.
Right,
And so we're going to force this one here.
right.
We're going to force this one here, this one, and this one. Okay? So now at this point, this can force back this way,
Right, right.
but these 4 vertices never become blue. There's nothing they can do.
Oh, I see. Okay, good, thanks.
Good question. Okay, so now we're going to talk about propagation time, and you should have in mind the 3 different kinds of zero forcing here. So the standard, the positive, semidefinite, and the skew, that's what R is. The color change rule is either the standard, PSD, or skew. In the R propagation time, we've taken the propagation time perspective. We're performing zero forcing in a propagating way, and we're just proceeding through, and the propagation time of a particular set is the least t such that we've colored all the vertices blue at B super t, and this is called the number of time steps or rounds to color the time. But then, so this is the propagation time of a set, the standard, PSD, or skew propagation time of a set. The propagation time of the graph assumes you start with a minimum R forcing set. So this actually has the downside that while these numbers, so I should have mentioned going back to these different kinds of forcing, it doesn't show up so much here, but you will see sometimes that the skew or the PSD is lower than the standard. So sometimes we have agreement, but certainly in the trees that we saw, if we go back to those trees, the zero forcing number on skew was 2. The zero forcing number of this tree on PSD was 1, and the zero forcing number on standard was 4. So the skew and the PSD are always less than the standard, but they're not comparable between the 2 of those. And because the propagation time of the graph uses a minimum zero forcing set, it renders the propagation times all non-comparable. If you want to compare the propagation time of a particular set B rather than the whole graph, which picks the minimum forcing set, Then you have the comparability, and you will have, for any given set, that the propagation time will be, for PSD, will be at most standard, and for skew will be at most standard. And we'll see this as we go through this exact same example. This is what we did before, but now we're thinking of the number of rounds. For the standard, we start with 4. We have 1, 2, 3 rounds. For the PSD, we have starting with only 1 vertex blue, and so it actually takes more rounds, 4 rounds. And for the skew, we started with 2, and it takes only 2 rounds. Questions about that? So here is a slide that lists some of the propagation times. These are by no means all the ones that are known, but you can see here, and in our example, you saw how the propagation time was actually more for positive semidefinite because you started with fewer vertices. You also see sort of strange things happening here. So in particular, if you look at the path and the cycle and the skew. So for the skew, an even path is self-forcing with no blue vertices. You start, the 2 endpoints force in, and then the neighbors of those blue vertices can keep forcing in, and eventually you hit 2 blue vertices in the middle or a pair of white vertices that force each other, and then you force back out. But it does then take you about order over 2. On the other hand, if you start with an odd path, then you're going to put a blue vertex in. You're going to have to. It's not capable of self-forcing. And so therefore the propagation time goes down to n/4 approximately, because you're going to be able to run 2 separate double time forcing processes. So that's what I'm going to say about propagation time. Are there questions on propagation before I go on to throttling?
I was wondering, is there a relationship between the propagation time and the minimum number, the forcing number? In other words, as with the paths, when you have to have an initial blue vertex, then it divides the time by 2. And you might say, okay, we're going to take some number and divide it by the initial size plus 1. Is there any meaning to this sort of thinking?
Oops. So there is, for standard, the propagation time of a graph is less than or equal to the order of the graph minus the 0 forcing number of the graph, because you're starting with this many blue vertices and you must perform 1 force at each time, or if you can't, you've stopped and it's never going to restart. So this is a sort of common bound that covers all of the things I could have written here. Positive semi-definite or skew, same rule. So this direction, that applies to all of them. But then there's something very special for the standard that doesn't apply to these other 2. And that is that the 0 forcing that the order of the graph minus the 0 forcing number over the 0 forcing number is a lower bound. And the reason that this is true is that standard 0 forcing can be thought of as a process of forcing chains. So there are other edges in the graph, but I'm only writing down the ones that are showing forces. And these are our initially blue vertices, and each of these performs 1 force. So the best we can ever do is to have all of these things run in parallel, simultaneous. And you see here, if I start with 9 vertices, I take out the ones that were blue originally. So I get 9 minus 3 over 3 is 2. And that's what you see, 1 step, 2 steps. That's the absolute best you can do. And that lower bound has a really profound impact on throttling, which is the next thing we're going to talk about.
But this lower bound doesn't seem to agree with the odd path case.
Are you talking about skew? I said this doesn't apply here. It applies
I'm
only
not
to
sure.
standard.
I don't know what I'm talking about because I don't remember.
I'll screen share, and I think we'll see that I was talking about skew, which maybe I wasn't clear about.
If you can bring that back up.
Yeah, so here it is. And
that is skew, okay.
Yeah, this is skew here.
So for skew, is there a reason why the odd paths are half the even paths?
Yes, because
beyond the fact that you split the path with one vertex.
The reason is because the zero forcing numbers are different. And the zero forcing number of an even path, skew zero forcing number of an even path is 0. And the skew zero forcing number of an odd path is 1.
I know, but that's just a vague general statement. Is there any precise statement about how the zero forcing number is related for different graphs? In the way that the fact that you start with a central vertex in the odd path reduces you to the to a different case, in a sense.
Now, this is really pretty path specific and certainly tree specific. The only general statement is that in general, if you, it's not an absolute rule, but for a particular family of graphs, if there's like an even odd parity and one of those requires a larger zero forcing number, then in general, this is not an exact statement, but in general, the one that requires more zero forcing numbers will run faster. More zero forcing vertices, a higher zero forcing number will run faster. Less propagation time.
But that's a much weaker statement than what you see with the paths where you actually divide by something. You don't just subtract something. Okay, thank you.
Yeah, we're going to get into this more in throttling. There is no exact relationship except for very specific graphs like paths.
Okay, thanks.
So throttling actually builds on the idea that we've just been discussing, which is that if you add more blue vertices, can you reduce the propagation time? Can you speed up the coloring process? So the idea here is you want to minimize some combination of the resources you use, whether these are phase monitoring units, and the number of rounds or propagation time that it takes to accomplish the task. And we often start with a larger set of blue vertices. And we say that the R throttling number, and here we think R is standard, PSD, or skew, of a set of vertices is the sum of the number of vertices and the R propagation time. And the R throttling number of the graph is the best you can do over all sets. Now, here, when I write B as a subset of the vertices, I'm actually allowing in sets that I don't really want, which are not zero forcing sets. And the way we address that is we say, if they can't color the graph, your prop time is infinity. So they don't enter this equation in any meaningful way. So we've actually have information we need to compute the throttling numbers of some of the graphs, because it happens that in this particular example, this is the best we can do. I have not proved it, but we do know that the throttling number of this set of blue vertices is 7, because there are 4 blue vertices, and the propagation time of this set when we colored it is 3. And these numbers represent the step in which the vertex turned blue. So you remember this one turned blue in the first step, this one turned blue in the second step, and so on. And for PSD, we can do better on throttling if we use 2 vertices. So if we use 2 blue vertices initially, then instead of having 1 vertex and propagation time of 4, which is a total of 5, we can, with 2 blue vertices, we can color the entire graph blue in 2 steps. Because remember, for PSD in a tree, you color every neighbor in each round. So what we're looking at is here, the 2 radius of this graph is 2. And for skew, the best we can do is what was this minimum skew forcing set, because it did it in 2. And again, the skew throttling number is 4 there. So here we have a slide with a bunch of throttling numbers of families and a little more commentary in some cases. So for the complete graph, the throttling number, and this is a typo I see right here. This should be, oh no, I take it back. It's n-1, because for standard, you have to fill in n-1 blue vertices, and it takes 1 step to color it blue, or you fill them all in. And here you fill in n-2 and you color the remaining 2 in 1. Isolated vertices, you have to color them all. Complete bipartite path. But what's really interesting here is this, for a path, you have stuff related to order of root n. So in the case of standard, it is that lower bound that I described to you that's playing a critical role. And for the skew and the PSD, these are very path specific, having to do with everything is degree 1 or degree 2. And the same thing for cycles. So somewhere here, yeah, this is a slide I want to talk about. So this is a lower bound on throttling number. Michael Young and Steve Butler proved that the throttling number of a standard throttling number of a graph is the ceiling of true root n-1. This is achieved by the path. And this comes from that inequality that I showed you, the lower bound on the propagation time. So then you can optimize the sum of the number of vertices used in the propagation time. And this bound that I showed you on propagation time, which I will just put back here for a minute, this actually isn't limited to just the propagation time of the whole. You can do this as the order of the graph minus the cardinality of the blue set divided by the blue set. Cardinality is less than or equal to the propagation time of that set. And this is what is playing the role in the Butler-Young theorem in throttling. And because of the very limited degree of paths and cycles, we got values that were not all that different asymptotically for paths and cycles, but we see that the throttling number of the star, PSD throttling number, is 2. You take the center vertex blue and then you propagate in 1. And the skew forcing number of any graph, corona K1, is 0, and the propagation time is 2, so the throttling number is 2. So there, you can have arbitrarily large graphs with throttling number 2 for propagation for PSD and skew. And then we did have this, a couple of slides in here that I skipped over to do a little bit different order. This is the list for the families that I mentioned. And then here are some relationships. So a positive semi-definite forcing set and a skew forcing set. Any standard set is automatically a PSD or skew. So we have these relationships that I mentioned with these numbers earlier, the zero forcing numbers. We have the propagation time of the set relationship, and therefore the throttling number of the set, and therefore we have the throttling number relationships. PSD throttling is less than or equal to standard. Skew throttling is less than or equal to standard throttling. PSD and skew are non-comparable, but the propagation times for standard, skew, and PSD are non-comparable because the number of vertices you're using differs. One of the things that gets studied for all of these, not just throttling, is extreme values. So there are here in the slides some of the extreme values for throttling, but I'm not going to go through these in detail. And I just want to mention that there is Sage software that computes all of these things. The forcing numbers are currently out there. I have software that computes propagation, and by say out there, I mean published on the Iowa State University Sage server, publicly available. These are all available from me on request for an SWS file, but because I'm still developing these by compiling other people's code, I'm just writing the workbook that calls other people's code basically, but assembling them into packages. These are very nice for experimenting. And at that point, I think I will stop and thank you. And there are references in here, the ones that are listed in the slides. So I'm going to send the slides to Sandra after I make a correction, and then she will be able to post these. Thank you.
Shall we thank the speaker in the weird Zoom manner? And then I will stop the recording and we can ask questions. Thank you very much, Leslie, for that wonderful talk.